So, in the last class we looked at, for the wedge solution, we looked at the momentum part. Now it is time to look at the energy part of the equation. So, the energy equation can be taken as, okay, theta is equal to T minus T naught by T infinity minus T naught, that we said earlier, right. T naught minus T infinity is basically given as C2 x to the power of n. We do not know the functional form because they may not have the same functional form as your velocity. Okay. So, therefore, T naught rather T is given as T naught plus C2 x to the power of n 1 minus theta, right. Okay. So, dt by dx is equal to C2 into n x to the power of n minus 1 minus theta plus C2 x to the power of n minus d theta by d neta into y C1 by gamma m minus 1 by 2 x into m minus 3 by 2. Okay. Okay. So, it becomes equal to C2 x to the power of n minus 1 n into 1 minus theta neta m minus 1 by 2 okay. Similarly, your dt by dy, if you do follow the same course of math, d theta by d neta to u infinity gamma by x. Okay. So, you understood what we did. Okay. So, it is pretty much just substituting u infinity as and when it is required, right, because remember u infinity is still given by C1 into x to the power of m. That is how this m comes into the picture, right. Okay. So, similarly, delta square t dy square is given by C2 x to the power of n d square theta d neta square u infinity gamma into x. Okay. Now, once again what we need to do, because your energy equation is dt by dx plus v dt by dy is equal to alpha delta square y by dy square, correct. Okay. So, we already have evaluated this. Okay. We have already evaluated this, we have already evaluated this, and we already know what is a functional form of u and what is a functional form of v from our earlier momentum analysis, right. So, it should not be a problem. Now, what we do is now put all these terms together, okay, because the new terms we have already evaluated in the same way that we did earlier. Okay. So, the final form becomes let me just okay. Now, if m is equal to n equal to 0, typical flat plate boundary layer solution, okay, what we get is theta double prime this equation will boil down to this particular form, which is the correct one, as we already know from our other analysis. Now, if n equal to m, that means the temperature and the velocity, external temperature and velocity has got the same functional form. Okay. This equation will now become theta double prime plus half Prandtl number m plus 1 into f theta prime is equal to 0. This is the expression that we also used in our suction and blowing. So, your Nusselt number will be equal to theta prime 0 into Reynolds number to the power of half. Here what has happened is that Prandtl number has been substituted by Prandtl number as m plus 1, right. So, it is like a pseudo Prandtl number. Okay. So, Eckert actually integrated it integrated this. Once again, this kind of thing has to be solved by knowing what is the functional form. Integrated it with theta 0 equal to 0 and theta infinity is equal to 1. Okay. So, if you look at the presentation format once again, okay. So, this is basically the expression, okay, and the line that it's given as a solid line, okay, that is basically the correlation that you are most experienced with, okay, is plotted with terms of Prandtl number, okay. So, as you can see in this particular configuration, once again you have beta equal to 0.5 and n equal to 0, beta equal to 0, n equal to 0.5, okay. So, these are, do not be bothered about the constant heat flux and the constant boundary profile, it is not the point over here, but you can see that this is plotted with respect to your Prandtl number. Okay. So, Prandtl number greater than 0.5, the correlation works pretty well, okay. Basically this 0.332 into Prandtl number to the power of 1/3 correlation works pretty well, okay. You also can look at table 2.3 of Bejan, okay, in order to see that what is the solution for theta, okay, what is the solution for theta for different m, okay. So, that what we are going to do in the next class, we are going to give you a chart in which we are going to say that this is the table which contains all the values, okay, of beta, okay. So, based on this, okay, based on this we have pretty much finished the case of Faulkner scan, with the exception that I will provide a table which may be which will be added with this particular class, where we will say that what is the basic case of basically suction and blowing, what is the m parameter all about, right. Okay. Now, without in order to finish off the external flow, okay, there is one more thing that we need to address, which is called the arbitrary wall temperature. That means this is a very specialized case, and I will show you what that specialized case is. Okay. Say for example, this is your generalized flat plate, okay. This is how the boundary layer actually develops, okay. So, say in this particular portion between x1 and x2, okay, between two limits of this particular profile, okay, the temperature is Tw, where Tw is greater than T infinity. On the two sides of the plate, this is still T infinity, understood. So, it is a plate in which only one segment of the plate is actually at a higher temperature than the incoming flow field. The other part of the plates, okay, are at whatever temperatures. In this case, it is the same as the ambient, okay. So, if the temperature was the same as the approaching temperature, you know quite well that there will be no velocity profile will be developed, right. There will be no velocity profile that will be developed if the profile is the same, right. But however, in this particular case, there is one section where the temperature is a little higher, right. So, it is almost like this. In this particular section, the temperature is higher, exactly like that, okay. So, what you are going to have if the plate was heated from x1, right, say entire plate was at a temperature Tw, right, you would get a boundary layer which will start developing from here, right. Okay. Similarly, if the plate is it's heated from x2, you will actually have a velocity have a thermal boundary layer which will develop from there, right. Let's call it delta T1, this is delta T2, correct, okay. So, you note one thing, one important thing when you solve this particular problem, that the integral energy equation that we did, right, energy equation is linear in temperature, isn't that so? It is linear in temperature, okay. Hence, to solve this particular problem, we can apply the method of superposition, okay. We can apply the method of superposition. Superposition is allowed for a given velocity field. See, the velocity field is unaltered, right, because it is a one way coupling, as we said. That means the The change in the density has got no effect on the temperature. So the integral energy equation is linear in temperature, and we can apply the method of superposition, okay. Because it is linear, we can apply the method of superposition provided we know what is the velocity profile going to look like, right. So this is the way, say for x1, this is one of the velocity profile, one of the temperature profile, this is the velocity profile, right, that develops regardless, right, that is delta, right. So this is the first temperature profile, okay, where this is Tw, okay, which is a plus delta T effect. Delta T is basically T wall minus T infinity, okay. I am summing it, okay, with this particular profile. Once again this is still delta. Now it is x2, right. This particular profile has got a temperature like this, right, which is delta T2. Now this temperature I am taking it as minus delta T, right, because here we have a plus delta T added throughout the length of the plate, right, is plus delta T throughout the length, but in reality only the portion x1 and x2 is the only portion that is heated. So therefore from x2 if we take a profile which is minus delta T, then basically you are taking into account the effect of that, basically you are subtracting that effect out from the whole picture, right. So therefore if this is the situation for x1, x greater than x1 less than x2, H will be given as k by x into 0.332, Prandtl number 1/3, Reynolds, this proportion remains the same regardless, right, okay, 1 minus x1 by x to the power of 3 by 4 to the power of minus 1/3, okay. 1 minus x1 by x to the power of 3 by 4 minus 1/3, q double prime is h into delta t, that is given as k by x 0.332, Prandtl number 1/3, Reynolds number half, delta t 1 minus x1 by x to the power of 3/4 raised to the power of 1/3, okay. This is for this region, right, for x when it lies between x1 and x2, right. For x greater than x2, right, your q double prime becomes k by x 0.332, again Prandtl number 1/3, Reynolds number half. Now it becomes a little bit more complicated, okay, because now you have the effect of the previous one as well as now you have this minus delta t effect as well, right. So it is 1 minus x1 by x to the power of 3/4 to the power of 1/3 minus 1 minus x2 by x, sorry, three-fourth raised to the power of 1/3. This entire thing is multiplied by delta t, okay. Let me write it maybe in a more proper form. So q double prime is equal to k by x 0.332, Prandtl number 1/3, okay. So that is the expression that you get in together, okay. So is basically a reabsorption of heat in the heated section, okay. Now if there are n such step changes, it is possible, right, you can have n number of step changes, right. So you can have situation like this, right, x1, x2, x3, x4 like that continued, okay. So you can have step changes like this, you can have any combination that you want, right. So, if there are n step changes, it becomes a summation now, okay, I equal to 1 to n delta Ti 1 minus xi by x to the power of 3/4 1/3, okay. This is the step changes. So, you can add all the steps depending on whatever it is, like delta T1 is negative, positive, you can do it in whatever way that you want, right. Okay, now, if there is a smooth variation, q double prime will be given as 0.332 k by x, Prandtl number 1/3, Reynolds number x to the power of half 0 to x dt 0 by d neta by neta. This is the dummy variable, okay, 1 minus neta by x, this is only raised to the power of 3/4 and add 1/3 to the top of that, right. So, this actually shows you that this is how the, for any type of temperature profile, that means if there is a variation in the temperature profile that we have across a plate, you can actually represent it in this particular fashion, right. Now, what to do if there is a similar situation in which we have a uniform heat flux kind of a consideration, okay. So, how to add those things also, okay. So, that will take a little bit of time. So, what we are going to do is that we are, remember last class we actually posed that what happens when there is a uniform heat flux situation, right. If you recall, that is what we did in the last class, where we said that if there is a uniform heat flux, the integral formulation, how it can be done. Do you recall that that was what we actually did? Now, if that is the case, what we are going to do in this particular class or in the next class, that we are going to look at that particular solution. Hopefully, you guys have already done it by now. So, you can cross check that what will be the answer. But in any case, if there is a, let me just give you the general profile for a uniform heat flux consideration. When there is an unheated, again there may be an unheated section, right. This is delta, still goes up as it is, okay. From x1, okay, you are pushing in a uniform heat flux, right. Let us call that Qs double prime. So, you are pumping in a lot of heat flux, okay. After say not x1, say it is x, this distance is say from here to here, from here to here it is x naught, right. Now, this is no dissimilar than the problem that I gave you where the uniform heat flux was everywhere, right. So, in this case the answer will be, the Nusselt number will be 1 minus x naught by x raised to the power of 1/3, Prandtl number 1/3, Reynolds number x to the power of half, right. When x naught is equal to 0, which is the case, which is the exercise that I gave you, okay, the Nusselt number is 0.147, Prandtl number 1/3, Reynolds number x to the power of half, right. Now, in the next class we are going to look at how we got this before we wrap up this particular section, right, that how we got this particular profile, because we did it only for uniform wall temperature. I gave this as an assignment. So, we are going to do it in the next class and show that how this thing actually works. While on the other hand, for any unheated starting length, this is the form that you are going to use, right. That means, if there is an unheated starting length, a portion of it there is no heat. So, in that case this is the profile that you have to follow, right. So, this actually completes. So, what we are going to do as a part of this lecture, we are also going to show you that table which shows that how the Nusselt number and other thing varies with m, okay. So, that is still remaining that we will add, okay. But in essence the entire external forced convection is kind of complete. with the exception that we are going to just do the uniform heat flux case, which were given as a homework problem. I am going to just do it here so that you can cross check that whether you are on the correct path or not. Okay. So, using this is where we wrap off. Okay. We are going to look at internal forced convection from next class onwards. So, just to add, as I was stating that if you look at that when there is a flow over a wedge, we wanted to know, for example, what will be the local Nusselt number values, okay, and that is exactly what we are putting up over here. So, if you look at the at this list, okay, so this is your beta, the one that we said is the wedge angle. This is the corresponding transform variable, which is m over here, okay, and these are the different Prandtl numbers. So, this is Prandtl number less than 1 regime, this is Prandtl number greater than 1 regime. So, as you can see, beta equal to 0 corresponds to the flat plate situation, right. So, Prandtl number equal to 1 is 0.332, as we knew earlier from our similarity transformation. So, this is for different sets of Prandtl number, what are the different values that you get, okay. So, similarly m equal to 1 basically corresponds to the Hyman's flow condition or the stagnation flow. So, those values are also given over here. So, as you can see, the Nusselt number seems to be a function of the Prandtl number, okay, for all the wedge angles, but as you can see that as we increase the wedge angle, okay, that means you are going into a more and more convergent nozzle kind of a situation. That means the flow is accelerating a little bit more, okay. You can see that the value of your Nusselt number correspondingly increases, right. So, this is kind of obvious, the same reason that we explained earlier, that when the flow is accelerating you have a very thinner boundary layer. So, that means your Nusselt number or your heat transfer coefficient should actually go up, right, because it is inverse of delta T, right. So, this is what you have an increase in the Nusselt number as you go on increasing the beta. So, this is what I wanted to show you guys, okay, and this is once again the same table, okay, when you actually have suction. All these are taken from Bejan. So, you can take a look at Bejan and you can see that you can study these different types of tables. For example, here of course, what we have done in one particular table, you have the Nusselt number, you have the skin friction coefficient, and this is have the blowing. Okay. This is of course over a permeable isothermal plate. There is no wedge angle over here. Okay. So, wedge angle is 0. Okay. As you can see that suction and blowing, how does the Nusselt number values varies, okay. You can easily see that, okay. So, as you know, when it is suction, the boundary layer is pulled inwards. So, naturally you have an increase, okay, and it is pulled out, it will go to 0 at some point because of separation. So, this is basically separation all around, okay. Similarly, for an isothermal edge, okay, if you have suction and blowing, that part we did not cover in details, but this table you can still study, okay. So, why some of the data are disjoint? Because not all the experiments were done, not all the analysis were done for all the cases, okay. So, that is precisely what it is. So, it is a wedge where you can actually have suction or you can have blowing. So, that kind of a situation, okay. So, all the data are basically compiled over here. Once again, if you look at the class of the data, you will see that obviously they also make the same sense, because here you can see this actually decreases, okay, for the same reason, because your blowing is actually increasing, correct, okay. For any given condition, you take any set, any m in this particular series, you will find that it is actually going down, okay. So, the wedge, we already know what the wedge angle does, right. On the top of that, if you have suction or you have blowing, you are basically additive or subtractive kind of an effect, okay. So, that is what is happening. Moment you have blowing, you reduce the Nusselt number value, because you are increasing the boundary layer thickness in a relative basis, on a relative basis. For example, this is the boundary layer, this is the Nusselt number for no blowing, if you look at this part of the thing, right, as you go on increasing blowing, this actually reduces. Okay. How much it will reduce, that depends on the calculations, that depends on the boundary layer profile. This is done for only one Prandtl number. You can do the same for other Prandtl number also. Prandtl number of 0.7 is roughly equal to that of air. Okay. So that is how this thing has been constructed. So we end this particular lecture where we actually have shown that with wedge, okay, what are the different values of Nusselt number, because we cannot solve the equation exactly. So we have to show you the end results. Okay. And also we have shown that, for example, when you actually have suction or blowing, what will be the values of the Nusselt number, and when you combine these two effects together, suction and blowing and wedge effect, then what do you get. Okay. So all these things are kind of narrated in the table form, and all of them make common sense. Whatever we argued about the boundary layer, all of them make sense when we actually solve it, and the value seems to agree with our intuitions. Okay. So we end this. Before we, now in the next lecture we will go to internal flow, internal forced convection. Thank you.